Hello, YouTube viewers. Welcome to my show, Science Thursday. In today's episode, we're gonna take a look at nuclear fission power. So let's dive right into it. So what it is very simple. It's E equal to mc square. Many of you know about this guy known as Einstein, and this equation, the most famous scientific equation there is, E equal to mc square. Is there a use of it? Yes, nuclear power relies on it. And what is actually happening is, like, you must have heard this time and time again, that you cannot create energy nor destroy it. However, energy can exist in different states. One of that state is matter itself. So this is what that equation is. The energy content of a matter, like iron, steel, anything, basically energy content of a matter can be extracted, and the quantity of energy that you will get is equal to mc square. So m being mass, generally, if you want to do the calculation, is generally done atomic mass unit, very small units, and c is constant speed of light, and square. So it gives you a very large amount of energy for a very little amount of matter. So basically, if you can successfully convert even 1 milligram to 500 grams of nuclear fissile material into energy, that's a lot of energy, like like tons and tons of coal equivalent of energy. And then you have to understand the fission that we are referring to. It's simply breaking something down. If we are breaking it apart, we are not building it like fusion, we are breaking it apart. Now generally, if you have seen the periodic table, on the bottom row there is a lot of heavier elements. Those elements are almost what you will call unstable. Now of course, not every element there is unstable, but if you, like, let's say take uranium, you add one neutron to it and it becomes from 235 to 236. It becomes unstable. Basically, the energy content of it becomes unbalanced. It wants to stabilize itself, like how you heat water up. It wants to reach equilibrium level. So something of that nature happens, and then it's like boom, splits. Now while it splits, it gives off 3 neutron and it gives off 2 remaining elements. However, very little amount of mass is destroyed in this process. So that mass you will not able to gain back if you recombine the neutrons and recombine the elements. That lost mass is converted into energy. That's your source of energy. That's what's giving you a lot of heat. So if you hear somebody say nuclear bomb gives out too much power, that's why it's giving you that much power. It's because matter was converted into energy, not chemical reaction, not spring mechanical reaction. It's simply matter itself was converted into energy. So how does nuclear power plant work? Well, there are very simple stages of it. There are 4 core stages. You take the fuel, fissile material. It could be anything. It could be uranium, it could be plutonium, it could be thorium. However, be mindful, the fuel used in nuclear power plants are very low enriched. Basically, they only refine it up to 20%. To weapons grade uranium, as you keep hearing in spy movies and all that, is like weapons grade uranium. What does that mean? It's simply the quantity of fissionable fissile uranium is very high, as in, like, what you mine out of the ground is very little. Like if you take 1 ton, you will barely get 1 kg that is fissile. We do a lot of process of refining it to make it more fissile. And what we put in the nuclear reactor, as you can see in this what we call fuel rod, they are only refined to 20%. So inherently, no nuclear power plant can go kaboom, because to make kaboom, we actually put something upwards of 80 to 90% refined uranium. So if you see any movie where they are saying nuclear power plant gonna go boom, yes, it can explode, but the explosion would be either steam explosion, water explosion, but it won't be a nuclear explosion, because inherently the fuel used is very well, I would say dirty, because it's not refined enough. And if you're like, what if somebody put a dirty fuel, the moment they put it, it will blow up. So unless somebody is trying to commit suicide, I don't think it's doable. Then we take the fuel, we put it in a reactor. As you can see, there are hundreds and thousands of reactor design. Now, one you have to be mindful, the most common design is what's called pressure water reactor. What does it simply do is basically, as you can realize, nuclear reaction is very hot. It can easily go up to 3 to 500 degrees Celsius. Now you might be like, okay, that's not very hot. You have to imagine 3 to 400 degrees Celsius of 10,000 liter of water. That's a lot of joule. And the bigger the pool, the basically bigger the reactor mass, that 300 degrees Celsius represents a lot of energy. And you are cooling it. It's not like, if you let it stay there, of course the water is going to boil off some point or another. But to make sure that water does not boil off because it's above 100 degrees Celsius, what we do is pressurize it. Once we pressurize this to whatever psi is needed, once you pressurize it, it reaches a point where it will not boil off even though it's above 100 degrees Celsius. It happens on sea floor also, where you can see the volcanic undersea volcano. The water there is not boiling off simply because of the pressure. So if you have a lot of psi in your water, it will take a lot of energy. Like to boil off water in this sort of scenario, you have to heat it up to like 600 to 700 degrees Celsius. Now the reactor can easily go that hot, however we are taking that heat away. That's the whole point of running water into the system. Now we take that heat away, and generally we run it through what's called steam cycle, as you can see by these things. You will see this in coal power plant, in gas-fired power plant, in nuclear power plant. They are the same. This just taking heat, turning it into steam to mechanical work by a generator, from generator to electricity, and that's it. So from heat part, it's completely similar. However, most power plants will generally don't have to worry about anything other than this part. But because nuclear power plants, as I told you, it creates two elements. Those two elements are very idiotically radioactive, as in dangerously radioactive, as in it will kill you in hours. So they also have to figure out how they're gonna handle the waste. As of now, we do not have any proper way of handling this waste. So what are the dangers of nuclear reactor? First danger is it's weaponizing. Now you might be like, okay, as I already said, the reactor itself uses very low grade fuel. However, the technology needed to reach that point is inherently more complex than what you need for a weapon. So if you can make a nuclear reactor, you can make a nuclear bomb, and you can use what's called enriching process, where you will take something that is non-fissionable and you will make it fissionable, and you can use that in your bombs. And you can make plutonium. Plutonium is a man-made element. It's not naturally occurring. You cannot just go and mine plutonium. You have to mine uranium, make it into plutonium, then you can use that into a bomb. So that's why the weaponizing potential of a nuclear reactor is ludicrously high. So that's why people like America, Russia and all that, they don't want every other country to have nuclear power plant, because inherently the technology needed for bombs and power plants are same inherently. And you have to understand, if you commit a mistake while you're making a nuclear power plant, or like Chernobyl, there is no fixing it. Like dams are also very dangerous. Like when dam collapses, it can kill 60, 70 thousands of people and destroy millions and millions of property damage. But over time it fixes. Here there is no fixing it. You have to get it right in the first go. If you screw it up, there is no fixing it. And the consequence, this is the most horrifying part. Like as I told you, if a dam goes down, you can have a scenario where you have catastrophic damage. However, it will not be for centuries. Nuclear power plant will be like for thousands of years. So if this is so dangerous, so difficult, what are the pros of it? The pros is that it is independent from environment. Like let's say, take example of India. India gets a very sizable chunk of its energy from hydroelectricity. Now, as many of you know, hydroelectricity is directly dependent on glaciers and rain. Basically, if you have too little rain, your power plant is not producing enough. But if your glacier shrinks beyond a certain point, yeah, your power plant is not gonna, like your hydro dam is not gonna provide power. So being independent from environment is very crucial. This also helps it to place, you can place this nuclear reactor wherever you want. Like wherever, like in middle of nowhere, in the sea, or like in middle of desert, you can do whatever you want with it. It's location independent. Then we come to the fact, the most dangerous aspect of our power generation is greenhouse emission. As you can see, this is, if you see those very big stacks, those are cooling stacks. They don't emit what you call exhaust. The exhaust, we will always see a very slim pipe, and it will be very tall. The chimney, the exhaust will be coming out from one. So if you see those big things, those are cooling tower. Those are not exhaust chambers. This is from exhaust chamber. So they give out carbon dioxide. Now inherently carbon dioxide itself is not dangerous. However, if you put enough of it in your atmosphere, it will create a cascade reaction. Basically, temperature will first go 1 degree up, 2 degree up, 3 deuterium, then methane that is trapped into everything, like in for case of humanity, in case of our earth, is trapped in what we call permafrost. Basically, once that leaks into atmosphere, methane is so dangerous, it makes a greenhouse effect of CO2 looks like a child. It's 20 times more powerful than that. That will trap more heat, releasing more CO2, releasing more methane that is trapped everywhere, and we'll keep burning more power plant over a period of time. As quick as 100 years to 200 years, we will reach a point where we'll no longer able to grow crops. Simply the temperatures will be too hot for any crops to grow. Our seas will be acidified to a point where all sea life will be destroyed. Now, not because that water became acidic, it's simply because the coral reef, like the feeding block of the basically lowest level of the food chain, will be destroyed. Now, once you destroy the base of a food chain, the whole food chain collapses. Same will happen. Like, we won't die simply because earth became a bit hot. We will die simply because we no longer can grow crop at the same rate. And you're like, okay, we're gonna do greenhouse makes it hotter, not colder. So for that reason, this is a very dangerous. Like, nuclear power plant does not damage the planet, this damages the planet. And you have to understand, every power plant technology that I have discussed, wind, solar, all those things, they have a limitation because they cannot act as a base load power supply. Basically, cannot go to a power company and like, this is my reactor, this is gonna give you, let's say, 100 megawatt of power, 24 into 7 into 365 into 5-6 years. You cannot do that with solar, you cannot do that with wind. However, with this you can do that. Even in dam, like hydropower plants, they have to be very big reservoir just for that reason. So they have a contingency. Let's say rain happens a little less this year, they can handle it. But of course, again, even this power plants are also breaking down. In California, dams are also losing their power because of the drought. So for all things combined, this can provide continuous uninterrupted power. Now, what are the cons of the situation? Cons is very simple. You have to realize the fission itself is not that big of a deal. However, the elements that it creates, those are idiotically dangerous. And of course, depending on the reaction you are using, either you are using plutonium or uranium or thorium, whatever you are using, the outcome will vary. However, in all scenarios, they come out very radioactively dangerous. The best can we hope for is it's only going to be radioactive for 1000 years. Suffice to say, no empire has lasted that long. So if you bury something like this sort of thing, you bury it somewhere, 1000 years ago, let's say, passes, and somebody redigs it for any reason. Let's say somebody forgot, they redig it, boom, it's still dangerous. And it has no tolerance for mistake. Like, if you mess up a solar power plant, the worst you can do is damage the grid. If you mess up a wind turbine, the worst you can do is like collapse that wind turbine itself. But nothing inherently self-destruct. But if you do screw up like this is Fukushima system. Suffice to say, it's very, very dangerous, and human stupidity is the core aspect of it. Now, I specified that nuclear power plant cannot go boom because the fuel itself is not enriched enough to have a runaway chain reaction. It can sustain a chain reaction, but not have the technology to go runaway chain reaction. Then you would say, okay, what happened in 3 Mile Island? Human stupidity, control. Basically, somebody forgot the pump was overfeeding, not underfeeding. It's a very, very serious reason why the heck that happened. It's like the keys they have in the nuclear power plant, the old analog system where they had keys for it. They had a tag, a long tag for it. That tag covered a light that was saying low coolant. They did not realize there was low coolant, and if they had just turned it off, everything would have been good. But that was human error. As I told you, there is no tolerance for mistake. 3 Mile Island accident happened. After that, we come to Chernobyl, the worst nuclear disaster that ever happened. Now, Chernobyl, after the detail came out, after the fall of Soviet Union, once every single detail has been passed up, people were surprised this reactor even worked for that long. The amount of cost cutting was done to that was idiotically cruel, I would say. Like, because many of you know there is something known as Geiger counter. It tells the radiation level, so everything is good. Every nuclear power plant should have a lot of Geiger counters. Awesome. Here's the deal. And they have what's called mounted Geiger counters. Basically, the Geiger counter won't be moving. It will be mounted to, let's say, wall, chamber walls, reactor walls, things like that. It will be mounted, so you get a very accurate picture. You can't because if somebody is, let's say, bring out ceramic tile, it's gonna be be very radioactive. To make sure they're getting constant reading, they generally put Geiger counters everywhere surrounding the reactor and the power plant. They did not put a Geiger counter that goes high. Basically, if you have a Geiger counter, there is a rating 0 to 10. Now 0 to 10 was safe for humans, so they did not put a Geiger counter that could go 0 to 50. So basically, the best when the explosion happened, when the steam, the water coolant system failed, basically they're no longer giving fresh water or cold water, it start to boil off, and then when it's boiling off, it gets very hot because nuclear reactor is very hot. I told you it's 300 degrees Celsius because we are constantly feeding it. Now once you don't feed it, it goes as high as 3 to 4,000 degrees Celsius. Now once that happens, what's happening is something similar to electrolysis, and given the fact that control rods that they were using had a specific property, if you mix it with water at that high temperature, it's gonna split water and oxygen apart. It's almost like electrolysis. Consequence, it's gonna combine again, and boom. That's what happened in Chernobyl. That's why you can still see the building intact, because steam exploded. The water explosion was more or less like a rocket explosion, not nuclear explosion. There was no nuclear explosion. The danger, the damage, the harm to people came from the fact that they did not even build a containment chamber, because inherently when you build a nuclear reactor, you know that it could blow up, so you will build a chamber that will either seal it or will not allow radioactive particle to shoot off in the atmosphere. It failed miserably in Chernobyl. Then we come to Fukushima. Again, Fukushima was so stupid, because when Chernobyl came out, when people actually looked at it after the panic was ended, people were like, this was a miracle that it lasted this long. So the idea came to people's mind that it will not happen in Europe, it will not happen in the first world country, simply because we have much higher safety standards. And that was true. This was running for 40-50 years. Now, problem with Fukushima is that when there is a commission of people, a lot of people sign in to that commission, and they go around every reactor in the world that is civilian operated, and they check its safety and all, and they give you a recommendation like do this or do that. They went to Fukushima and they're like, everything is good, but your seawall, basically they were seaside, so seawall was not high enough. They told them, please increase the height of the seawall. It's very not high enough. A tsunami can easily flood this side. And all their backup generator, which they had 40 backup generator. 1 or 2 should be more than enough to run the system in backup mode, but they had 40. Awesome. Here's all the 40 was in one place, and all of the 40 were in a place that it could be flooded. So they got a letter, like a written letter from the Commission of Nuclear Safety, that please do this because this is a vulnerability. They said, we've been doing this for 40 years, we know what we are doing, and tada, it exploded. Now, this was a very well built reactor. That's why we did not have the same level of catastrophe as Chernobyl. Chernobyl still is the worst thing, and this could have been saved if they simply had backup generators placed different places where it cannot be flooded. Putting all of them in a place where it can be flooded was stupid on steroid. So these are the cons of it. Now, what do we see in the future is very simple. It's gonna be crucial for Mars project. Now, we cannot go to Mars on solar power alone. We need nuclear power, specifically if we're gonna be there on the surface. So flat out, if humanity is to go to Mars, they need nuclear power. No discussion about it. Then the reactor, you have to understand, what we built was very rush built. It was not somebody sat down, designed a system, then improved that design, then redesigned it. No, it was just like they come up with a design and everybody ran with it. General Electric started to sell nuclear reactors as a module, like you buy this 500 megawatt module, 600 megawatt module. As soon as the first designs were approved by the safety commission, there was no improvement done to it. So inherently many lame ideas that at the time made sense, but since now we know more, the design of all the reactors that are operational today is very inherently weak. It's like old diesel engines where when you started like boom, boom, that kind of old design. But modern diesel engine does not do that. That's the same reason. The design has improved a lot. However, all the reactors that we have operational is not those new current generation reactors. So there is a lot of room of improvement in the design factor itself. Then we're gonna use thorium, this element, simply because this has lower potential of weaponizing it, and the radioactive waste that it gives out can only last for 1,000 to 5,000 years, not 50 to 60 million years, not 10,000 years or 50,000 years. So that's the benefit part. Like if you bury it deep enough, the radioactive waste that it creates, you can forget about it. You can be fairly certain that over time it's not gonna pose a danger to humanity. And not to mention, Bill Gates is also spending a lot of money into this reactor technology. So there are a lot of innovation being done into nuclear reactor technology, and I really like the idea of salt reactors simply because, as I already told, every reactor blows up because water blows up. They're removing water with salt, and salt has this benefit that it will only remain liquid as long as it's 300 degrees Celsius. And some designs are so advanced that they have two reactors. One reactor is your power reactor, where you're getting the power. Second is a emergency dump reactor. So as I already told you, that reactor gets hot if you are not running coolant through it. So they built a second reactor simply because if meltdown happens in the first reactor, which will be on top of the second reactor, it will melt, the radioactive material will go in the second one and just cool down there. That reactor is specifically designed to make sure it radiates as much heat away as possible without causing any serious damage. So inherently, we can expect much safer design. We are planning to send it to Mars, so obviously, and thorium. So all things considered, I think nuclear is going to play a very serious role in our future. So this was my presentation on fission power. I hope you liked it or learned from it. In that case, please like. If you don't dislike it, and leave a comment what you want to see in the next episode of Science Thursdays. And please subscribe, press the bell icon, as I make video every day. And as always, thanks for watching.